Okay, so everybody, welcome back after the coffee break. Yeah, so we'll continue with our problem. So we're talking about closed loop systems and using generalized coordinates. That was too difficult. We had to cut the system open. We have more generalized coordinates. Now we have constraints. We can solve that. Then with a numerical integration we do an estimate, but it turns out that the estimate is not on the surface, and we have various ways to get back to the surface. So for instance, where if we have this estimate and it's not on the surface, we want to get back, but where on the surface do we want to get back? That is the big question. Well, a naive way is to say, well, we have this estimate. We have this estimate Q bar at moment 1, but we want the real solution, which we just will call Q1, to be on the surface. Now a naive way would be to say, well, it should be the shortest distance, right? So from this estimate to the real solution, we don't want to go this way or all the way back. That would also be a valid solution, but it doesn't really help us. So the shortest way back to the surface, that seems to be. So the shortest way of this solution minus the estimate 1, this should be actually minimal with respect to all these Qj. So we want to choose Qj such that this norm is minimal with respect to, subject to, of course, the constraint. Subject to, yeah, they have to be, oh, that's an I, should be 1, subject that this should be on the surface. So this is our problem now. This is the problem we have to solve. Now, if we didn't have this whole subsidiary condition, then to minimize this distance, yeah, that is of course easy. Then then Q should be Q delta, Q tilde, and then the norm is 0 and it's minimal. But we have constraints, so we have to solve it with the constraints. And how do we do that? Well, first let's do a linearization. So first we say, well, the real this real solution is this estimate solution where we do a small change delta Q. That's the small step we do. This delta Q is this small step we do back to the surface here. And then if we look now at our problem and then we substitute this, then actually our whole problem is that these cannot change and these this will change. So the norm of the delta Q1 should be minimal with respect to our delta Q. Our delta Q is now our variable. And of course we have, that's the C of this Q tilde plus delta Q should be 0. Now these are nonlinear equations, so now we're going to linearize these because those are the only solutions, the only problems we can actually solve, and nonlinear problems are almost unsolvable. So linearizing that means that we write instead of C Q tilde 1 plus delta Q is 0, we're going to linearize it, meaning we say, well, we have this C Q1 plus C comma with respect to Q, right, times this delta Q should be 0. We can put a 1 here. That is okay. Okay, so now we have from this linear, we linearize this. So this is the linearized equation. And we can write that in another form, because now to show that we have really linear constraints, we can say, okay, C, Q times this delta Q is minus the C in this thing. And yeah, you can say this is like the error in the constraints, right? Error in the constraints. Yeah. Now to solve this whole problem, minimization problem, subjected to constraints, there's a standard terminology for that. We call that the solution is found via and we call that a Gauss Newton process, and for instance, read Langsos. Read Langsos on that. I gave the reference to the Langsos book previously. It's not on Brightspace, but the reference is there. Anyway, if you then look at what the equations we get for that are, well, we get, of course, identity, then we get CQ transpose, we get C, the Jacobian, zeros. Then we get here our delta Q's. Then here we get multipliers, yeah, no surprise, because it's a constraint problem. And then here minus C Q tilde. So, which of course comes from this problem that we have this delta Q should be minimal with respect with respect to delta Q, or in other words, the square root of delta Q1 squared plus delta Q2 squared plus should be minimal with respect to the delta Qi, or in other words, yeah, meaning the delta Qi should be 0, right? However, that's also what we see in equations. I times the delta Q is 0, but we have constraints. So we have to add these constraints by means of this Lagrangian multiplier, which then end up as mu times this Jacobian. I'm not going to do the derivation here. It's in Langsos. I gave the reference in the book also. It's a bit tedious, but... And then, of course, those are the equations, the minimization equation, the solution to that. And then, of course, subjected still to the constraint. That is the second equation. So let's simplify the notation a little bit. Let's do it like a shorthand. Otherwise, I have all these tildes and things. Shorthand notation. What am I going to do? I'm going to write capital I. I'm going to write a C for the Jacobian, and the C here. Here are zeros. Then I call this just delta. It's a vector, of course. This is also a vector. Vector. And of course the Lagrangian multipliers are also a vector. And then on the right hand side I write a 0, and let's call this error, right? Minus E, where E is this error C of Q tilde. Okay, now actually if we have this system, we can easily solve that. Because, well, looking at the equation, just take the first equation, right? Then what does the first equation says? It says delta plus C transpose times mu equals 0. Oh, that's simple. So you can say, oh, I know what delta is. Delta is minus C transpose times mu. Okay, still I don't know what mu is, but for mu I have my second equation. I can write C times this delta vector equals minus E. And then I substitute my delta into the equation. And what do I get? I get that C times this delta, so I get minus C times C transpose times mu is minus E. Or in other words, I get the equation C times C transpose, so that is a matrix, times this vector mu is E. Now, C times C transpose, what is the dimension of that? So the dimension of the C matrix is the number of constraints. So let's take our example in this case, this 4-bar mechanism. Then we have 2 constraints, so it's a 2 by, and we have 6 coordinates, right? We have 3 rigid bodies. Yeah. So we have 6 coordinates. Well, in this case, we have not 6. We have 6 rigid body coordinates, but we have 3 generalized coordinates, right? Because we write everything in generalized coordinates. So it's a 2 by 3 matrix. So in the end, a C times C transpose comes down to a 2 by 2 matrix. And that makes sense, of course, because we have two multipliers and we have the errors in the constraints are two errors. So hopefully, and you will see in most cases, this matrix is invertible, 2 by 2, that should work. So we can write mu equals then C times C transpose to the power minus 1 times E. So now we found a solution for our multipliers. And then putting in our multipliers in the equation, we find our solution for our increment C transpose times C transpose minus 1 times E. So that is now our increment. And that is the answer to our solution, right? Or in terms of this, our delta Q1, what do we have to do to come to the correct solution? Then we have to do minus C transpose, where C comma Q, and that's the Jacobian, minus 1 times the constraints evaluated at the estimated value, and then we say, well, the updated value is now the estimated value. Ooh, that's not a nice slur. Go back. Estimated value plus our increment. And of course, these are all vectors, right? And that is the process. So now we have found a nice way to update it. Then we can check. Of course, we have to check how well are they on the constraints. And if that doesn't fulfill, then we just redo the thing a number of times, and then we really get back to the constraint service with this Gauss-Newton process. So this is a way to solve our whole closed loop system. So first we cut it open, we formulate the constraints, do the equation of motion, do an estimate with a numerical calculation, with a numerical integration, and then with this Gauss-Newton process we project back on the surface. We do that for the coordinates and also for the speeds. I will get in a second to that. And then if the coordinates and the speeds are back on the surface within a certain error tolerance, we say, okay, proceed, next time integration. So that is the way to go to solve these closed loop systems. Now, this whole process, this Gauss-Newton process, seems like sort of a magic thing. Like what magic is going on? So to show the magic, I will do an example. To show the magic. Let's do an example. And on purpose, I take the example is just a linear case. I could do a non-linear problem and linearize it, but in the end we have to linearize it, and that is the thing we solve. So let's start immediately from a linearized case or a linear case. So a linear case is as such. I have two equations. I have x1 equals x2, and I have the other one that is x2 equals x3. And I have a solution, an approximate solution, which is, so these are two constraint equations, which I can write, of course, in a constraint form. Maybe I should do that. So in a constraint form we get, well, you have to make a choice now. What did I do? Minus x1 plus x2 is 0. That's the first constraint. And then the second constraint was minus x2 plus x3 is 0. So this is the constraint form. And then I have an estimate solution, which comes from heaven, from somewhere, I don't know. And the estimate solution is, what did I take? Oh yeah, 0.911. Now clearly, this is not on the constraint surface, right? Because if you calculate what are the values for this, then so we take minus x1 plus, so that is 0.1, that's not 0, and the second one is 0. But still, it's not completely 0, so we have to put it back on the surface. So then we write our new position is our approximate one plus our delta x, right? Like in the derivation. And then we say we want to minimize delta x, minimize with the constraint of c times the cx is 0. That's the thing we're going to solve. And we saw in our derivation that the answer is, well, the step we have to take, delta x, is minus c transpose times c transpose to the power minus 1 times the arrow which we make. This is then the arrow which we should make. Okay, what is the matrix C? That's the Jacobian of our equation. So let's write our equations now in this nice matrix vector form. So x1, x2, x3 is, this is 0, and since it's linear equation, the thing which pops up here is the Jacobian then already. So it's minus 1, 1, 0, and 0, minus 1, 1. So this is C, Jacobian matrix. Okay, then looking at this, we have to form a matrix C times C transpose. So C times C transpose equals, well, let's write it out, right? We do an example, minus 1, 1, 0, 0, minus 1, 1, times this matrix, and we copy that minus 1, 1, 0, 0, minus 1, 1, equals, so we get a 2, minus 1, minus 1, and a 2, and I'm sort of happy with this result. Now, why am I happy? And then everybody in the chat said, because, well, nobody says anything in the chat, so I will say the because it's symmetric. And I expect it to be symmetric because if I take the transpose of this, I get exactly the same expression, right? Okay, so then we need the inverse of that one, so we need C transpose to the power minus 1. I learned a trick to do that. First, the determinant, so that's the determinant is 4, that is 1 over 3. And then this element is this guy. And this element is this guy. Yeah, it's all the same. And this element is minus this element, so that's a 1 and that's a 1. Now let's see if it works. So I just multiply this with this, so I get 4 minus 3 divided by 1, and this is perpendicular to this one, yeah, vice versa, so that looks okay. Then we put that in our equation here for what is delta x, right? So delta x is this minus, then the C transpose, so that is this minus 1, 1, 0, 0, minus 1, 1, times this inverse matrix, right? That's 1 over 3, 2, 1, 1, 2, times the error we have. Oh, we didn't calculate the error. Or did we? Oh yeah, we calculate 0.1 and 0. So that's point times 0.1 and 0. Yeah. And then the outcome is, if you do some calculation, and then let's assume this is a 1 for simplicity, then we only have to look at these two columns. This goes away. Remember, we have a 0.0 to track, so we put the 0.0 here. Forget about the 0.0. This column and times this matrix. So this times this, so we get minus 2 over 3 with another minus, so that's a plus. So forming 2 over 3, and then here a minus 1 over 3, minus 1 over 3. So that is apparently the solution. Yeah, okay, looks okay for now. Now the final solution is of course our estimate one plus our increment, which is 0.2 divided by 3 and minus 0.1 divided by 3 minus 0.1 divided by 3. Or in other words, that will become, oh yeah, this is 0.9 with a lot of 6's, and this is 1/3, yeah, so this is minus, with a plus, minus 0.9 with a lot of 6's, 0.9 6's. So the answer looks right, because x1 equals x2 and x2 equals x3. That was the beginning of our problem. I said, this is my problem, these are my constraints. Then, is it the shortest distance? That is the question. Shortest distance. Well, another solution would be, of course, 1, 1, 1. And then the delta x would be 0.100, right? So the question is now, is this larger than this guy? So to see if this guy is larger than this guy, we just have to take the norm. So what is the norm of 2, 3, 1/3, 1/3? Of that factor, so that is 2 times 4, 5, 6, so that's 6, and 3 squared is 9, so that's the square root of 6/9, which is clearly less than 1, right? So this increment is smaller than this increment, so the answer is yes, it probably is. Okay, so that is explained how our Gauss-Newton step works. And then finally, for our system, we had all these different steps, like cut open, more generalized coordinates, do the constraints, formulate the equation of motion, solve for the acceleration, do the increment, and now the coordination projection method, coordinate projection method, is as follows. And I write that now like pseudocode, right? Because all the theoretic things we derived, and now we can write down how we're gonna do that. So first we set a variable which we call iterat. We set that to 0 because we have to iterate. We have nonlinear equations which you have to linearize, and we have to keep track on how many times, because after a number of iterations you just want to stop. Then we have to set a tolerance, because we can never get 0. The constraints will never go back to 0, so we have to set some tolerance, what we call 0, so 10 to the minus 12 or something like that. And then in the first step, then we set the new coordinates, we set them to the approximate one, to the estimate one. That's the one. And then also we set the number of max iterations we have to a certain value, and you could now say, well, let's take 10. If we haven't converged back to this constraint surface in 10 iterations, there's probably something rotten in the state of Denmark, and it's not Ebola, it's something with the scheme, right? So then, or SARS or COVID or whatever, something rotten, we have to stop our iteration. So the first step is we have to evaluate our error. So evaluate what is the constraint. So the error, which is the constraint at this estimated position. Yeah, I underscore everything, okay, to show it's a vector. Then I have to make the repeat loop. And then I say repeat. And why do I underline these? Oh yeah, okay. Then I maybe should underline these also. Okay. Repeat. What do I repeat? Well, I'm going to calculate my increment, right? As being this. Yeah, I also have to evaluate C, which is C, Q, right? The Jacobian. So then I take minus C transpose times C transpose times this error. I calculated this error here. I have to increment my new coordinate is my old set of coordinates plus my increment. Yep. And then I evaluate again what are my constraints, what is the constraint value, Qn plus 1. And I have to determine what the Jacobian is. And then when do I stop? Until the error the norm of the error is less than the tolerance, or when the number of iterations is exceeded, right? So if iterat is larger than max iterat, then I have to stop. Otherwise you could be in this indefinite loop. Okay, so now I have new coordinates, but we also have to do this for our estimated speeds. Estimated speeds, because we not only have coordinates, but we also have speeds. So we have our q dot with a slur on top of it, n+1. And what are the constraints on our estimated speeds? So all the constraints on our estimated speeds are double punt. Well, they are linear, right? Because that is, we have constraints being c q is 0, ck of qj, and then we have for our speeds we have ckj, q dot j is 0. So these are linear constraints. Linear constraints. And that is good, because if they're linear constraints, then in one step we can solve that. So, go back. So then in a one step Gauss-Newton method, we solve for the correct speeds. So it's a one-step method. Very simple. We don't have to iterate or whatever. So if I would write it quickly down, and you could say, well, the real speeds at n+1 are then these estimate speeds at n+1 plus, and then we get, of course, our increment, which is our c comma q transpose, c comma q transpose to the power -1 times the values of our errors, which is c comma q times q dot a slur n+1. And maybe there should be a minus sign here. Yeah, there should be a minus sign here. Okay, but look it up in the book. But anyway, it's like a one-step thing. By the way, this strange way of this matrix, this C transpose C transpose -1 also has the name of C plus, or what we call the Moore-Penrose inverse, and that's also sometimes used in MATLAB when you use the backslash. Sometimes used in MATLAB, and you can also look it up in MATLAB, Moore-Penrose inverse, when you use the backslash for the matrix division, because you can also use a backslash for the matrix is not square, and then it finds a minimal solution, which is like a sort of a Gauss-Newton type of process. Okay, that was in a nutshell the topic of today. Please do homework 7, which is due in a week from now. On Monday it is King's Day, but there are office hours. Monday is King's Day, but we do have office hours. We do have office hours online. Office hours online, just like in Q3. There's a question from Sven. Would you repeat if this is Qn plus 1 plus delta is 0, then E will always be 0. Yeah, yeah. So there is this question in the what is it in the chat? Yeah, the question if the delta yeah, but we have constraints. So read about it. So there are constraints in the system, and the deltas the final solution has to fulfill the constraints. So therefore we have the Lagrange multiplier, and then it's a bit more complex. Sven, read all about it in the book. Okay, then I will finish. We're a little bit early in time, but that's when there's no audience, right? See you all next week when we continue with chapter 17, which is about non-holonomic constraints. And if you don't remember what non-holonomic constraints are, please read the first part of the book, where it's excellently explained by Heike what they are. Okay, see you all next week.